Well, I'm on the way, the time cold, I wanna be keeping you warm. I got the right temperature for shelter you from the storm. Hold on, girl, I got the right tactics to turn you on.
Hi everyone, welcome to the video lesson for Monday, March 22nd and Tuesday, March 23rd. Today we started our new unit, Unit 7, Thermochemistry. We start with a warm-up, which was one of our brainstorm type warm-ups where I asked you to tell me what did you think of the words thermochemistry, endothermic, and exothermic. I had a lot of really good responses, and again, it was not one where I wanted to see like the Google definition, but what you think when you see those words. So I'm very proud. Remember, my favorite ones are the ones that aren't quite right, but you were able to pick clues out of those words to make some inferences, and those are my favorite. I had a lot of good ones. And then we started part 1 of our thermochemistry notes, Unit 7 notes. And your homework is to finish the gizmo. Feel the heat gizmo. It's one of those gizmos where it tells you how to set up the experiment and asks you questions about what did you observe. So you can do a lot of this on your own. You don't really need the notes for this, but I figure the notes are going to help you out a lot. They'll help you make sense of some of what you're seeing. Once you've generated your own copy of your Unit 7 notes, please remember to hit that little folder button that says Move and put this into some sort of a chemistry folder so you can find it easily. I forgot to put Honors Chemistry in the name of this document, so it's going to be a little bit hard for you to find it just by searching through your Google Drive. So thermochemistry is the transfer of energy, usually is heat, that's what we're going to focus on here, during chemical and physical changes. Now, the most important guiding factor we have here is the law of conservation of energy. So the law of conservation of energy says that energy is neither created nor destroyed through any chemical or physical process. There is a set amount of energy in the whole universe. We can't create more, nor can we destroy what we have. So this has a few different implications. The first of which is that the total amount of energy in any isolated system remains constant. So if I'm looking at something like just one reaction and it's insulated from the rest of the world, nothing else is interfering with it, that amount of energy that's being transferred, that's being changed, is going to be constant. The total amount is going to be constant. And second, even though we cannot create or destroy energy, we can transfer it and we can transform it. So I can heat something up. If I put a pot of water on the stove, I can transfer heat from the flame of my stove into my pot of water to make it boil. I can also transform my energy. One of my favorite examples of this is a hairdryer. When I plug a hairdryer into the wall, electrical energy flows into it, and out of my hairdryer flows mechanical energy, which I can feel with the wind that it generates, heat energy, which I can feel from the warmth of the air that it generates towards me, and sound energy, which I can hear as soon as I turn it on. So I can change my type of energy, and I can transfer it from one thing to another. So what is energy? Energy is the ability to do work or to produce heat. It's the ability to move and interact with other things, or the ability to create warmth. Kinetic energy is the energy of movement. So anytime something is moving, rolling, running, any type of motion is kinetic energy. The other kind of energy is potential energy. Back when you took some intro to physics back in middle school, you probably remember that a ball at the top of the hill would have a lot of potential energy, but as it falls down the hill, it turns into kinetic energy, and at the bottom of the hill, you have no potential energy. That is true. Potential energy is largely the position of an object, but for us, we are concerned about the composition of an object. So how are those atoms bonded to each other? How are the molecules attracted to each other? So the composition of my different molecules in matter is what stores the energy for my potential energy of my compounds. So my energies and my chemical systems. Kinetic energy is coming from the constant and random motion of all the atoms and molecules in any sample. Go ahead and put your hand on a desk or your chair or the floor or the wall. Unless someone is jumping up and down nearby, it probably feels very still, like it's probably not moving. But the truth is, it is. The atoms, the molecules in your wall, in your desk, in your chair, in everything are constantly moving in random motion. The average of that random motion is its temperature. So even if you have something that's really cold, like an ice cube, there's still random kinetic energy in that ice cube. Those molecules are moving. Now, if something feels cold to the touch, that just means those molecules and those atoms are moving more slowly than the atoms in your hand. Whereas if you place your hands on your laptop right now, it probably feels warm. Those molecules in the plastic casing of your laptop are moving a little bit faster than the ones in your hand. The more movement, the higher the average temperature. The more movement, the higher the average kinetic energy is, so the higher the temperature of a substance is. As you increase that temperature, that kinetic energy is also increasing. And potential energy is energy that can be used or gained from chemical bonds between my atoms. If I increase the energy in a substance, that means its molecules are going to be moving faster and faster. That means its kinetic energy is going to increase. So let's go back to that ice cube. In my ice cube, my water molecules are moving. They are not standing still. But if I increase the energy, if I add more heat into my ice cube, those molecules will start to move faster and faster. Eventually, my solid ice cube will melt into liquid ice because those molecules have gained more energy. They're moving more rapidly. If I apply even more energy, those water molecules will go from liquid to gas. They'll boil off. They'll get more and more energetic. They'll move more and more quickly, and they will escape their intermolecular forces that are holding them together. Now, the opposite is also true. If I remove my energy from my sample, if I have some water vapor and I remove energy, those molecules are going to move slower and slower. As they move more slowly, they start to condense and get closer together, and those intermolecular forces start to rein them in. So as I pull more and more energy out, they move slower and slower. Their kinetic energy decreases as well until they're vibrating in place as a solid ice cube again. Now my potential energy in a substance. The chemical potential energy for any sort of substance comes from the energy that is stored in its chemical bonds. Anytime I want to have a chemical reaction, I have to break apart the bonds that already exist and then make new bonds for my new products. Anytime I'm going to break apart bonds, it requires energy. My molecules, my atoms, are perfectly happy in the state that they are in the molecules that they have formed. If they were not happy, if they were not satisfied, grounded, stable, they would not make those molecules. So if I want to unmake molecules, I have to put energy into the system. I have to put energy into it to break those bonds. Those atoms absorb that energy and become more energetic themselves. Now, this is a lot like our electrons giving off light energy back in the fall. When they absorbed energy, they went up to their excited state. They didn't want to be in their excited state, so they gave that energy back so they could fall back down to the ground state where they were more stable. My elements typically prefer to be bound to something else. So once I've given them this extra energy from breaking their bonds, they typically want to form new bonds. Once they've formed new bonds, they are more stable. They release energy. So whenever I make bonds, I am giving energy off. I am lowering the amount of energy. I am giving off the excess so it can be more grounded and more stable. So I can measure energy. Energy has units. I can measure energy in joules or calories. So 1 calorie with a lowercase c is equal to 4.187 joules, which is shown with a capital J. Calorie is kind of the imperial unit, kind of like feet and miles and pounds, whereas joules is my international scientific unit, my metric unit for measuring energy. Both of these amounts, 1 calorie lowercase c or 4.187 joules, is the amount of energy that is required to raise 1 gram of water, so 1 milliliter or 1 cubic centimeter of water, by 1 degree Celsius. Now, when I said calorie, most of you probably thought of food, because we know that food has calories. Well, 1 capital C calorie is the type of calorie we read about when we look at our nutritional information. 1 capital C calorie is equal to 1 kilocalorie with a lowercase c. So 1 nutritional calorie is equal to 1,000 lowercase calories. Now, a neat thing to do, if you are lucky enough to have international food in your home, go and look at some of those international food labels. Sometimes they have the calories run with a capital C calorie, but you may notice if you have food made from other countries, sold in other countries, sometimes they have kilojoules, kJ of energy. Sometimes they have kilocalories, kc. So it's interesting to see how other countries sometimes show their nutritional facts. Now, heat is a type of energy. Heat is the energy that's being transferred from one substance to another due to the difference in temperature. Whenever you see heat in an equation, it's denoted by the symbol Q. We're not quite sure yet if you're going to see many of those equations this year, but we want to make sure you're ready for it. Energy always moves spontaneously from matter with high temperature to matter with low temperature. Now here's one of my favorite mind-blowing facts from today's class. There is no such thing as cold. Cold does not exist. You cannot measure how cold something is. The only thing that really exists in regards to temperature is heat, is energy. I can see that one thing has more energy and another item has less energy, and I can say one is hotter and one is colder, but cold itself does not exist. Cold is a description. Cold just means it has lower energy than something that has higher energy. When heat transfers, I see a temperature change. For example, if I have a hot cup of coffee, that heat from my coffee is going to transfer to the air surrounding it or to my hands holding the mug of coffee. My temperature of the air and of my hands is going to increase. I'm going to see a change in temperature in my hands, and if I wait long enough, I will also see a change in temperature in my coffee. It will get colder. Its energy will decrease because the energy from the coffee will go into the atmosphere near my mug, into my mug itself, and into my own hands. So be careful. Temperature is not the same as heat. Temperature changes due to the heat transfer. Heat is just energy that's being transferred. Temperature is the average energy of a substance. So delta E is the change in energy of a system. So if I'm looking to see how much heat was transferred, I look at how much energy does my system have at the end and subtract how much energy it had at the beginning. So if I want to know how much heat energy my mug of coffee lost, I would look at its temperature, its average energy at the beginning, Then I would look at its average energy, its temperature at the end, to find out how much energy it changed by. If my system is properly isolated and insulated from the rest of the universe, my energy will remain constantly. What leaves my coffee would go directly into my hands and just the surrounding atmosphere. Now that's only in a perfect world. In the real world, our coffee moves around a room, so it will heat the air around it as it moves. It's heating lots of different air. So it actually releases a little bit more into not just the surrounding, but the universe at large. But if I have a perfectly insulated system, a perfectly isolated system, my energy transfer is complete between my system and its surroundings. Every time I have a chemical reaction, there is a change in energy that is associated with it. My exothermic reactions release energy, usually in the form of heat. My endothermic reactions are going to absorb energy from their surroundings. They're going to feel rather cold. Now remember, bond breaking requires energy. Bonds absorb energy in order to break them. But anytime I make new bonds, I release energy. So if my reaction is endothermic or exothermic, depends on if I'm requiring more energy to be sucked in to break my bonds, or if I get more energy from making new bonds. My example here are hot and cold packs. Most instant hot packs or instant cold packs usually have two containers inside them separated by a thin membrane. One side will have water, the other will have a salt. When you squeeze and shake, you break that membrane and you mix the salt with the water. Sometimes you get an exothermic reaction, which gives you a hot pack. Sometimes you get an endothermic reaction, which gives you those instant cold packs. So my hot hands pack, or an instant hot pack, would be an example of an exothermic reaction. It feels hot because it's releasing energy to the surroundings, probably to your hands. Heat is going to flow out of the system, so it flows out of the hot hands pack into the surroundings being your hands. Your surroundings are going to feel hot or hotter. Remember, energy, this is all kinetic energy, the energy of movement. Those molecules are moving very quickly inside of that exothermic reaction. I'm getting a lot of energy being released from those new bonds that are being formed. So that energy is going to go from the hot hands pack into your own hands, accelerating the speed at which your molecules and atoms are vibrating themselves. The instant ice packs, however, are endothermic reactions. They feel cold because they are absorbing energy from their surroundings. So if you hold a cold pack into your hand, it's actually a bit of an energy vampire. It's taking the energy from you for itself. So your atoms, your molecules start to slow down a little. Your average kinetic energy is going to decrease as it goes into the ice pack. So you are losing heat when something feels cold. Remember, cold doesn't exist by itself. Cold is just a change in temperature. It's a difference in temperature from a hot thing versus a cold thing. From something with more energy compared to something with less energy. So the heat is going to flow into the ice pack from its surroundings, usually your hands. And so the surroundings are going to feel cold or colder. Their molecules and atoms are slowing, so the kinetic energy is lower, so the temperature is lower. Then in most classes, we skipped all the way from slide number 10 all the way to slide number 14. We're going to backtrack a bit later, but I feel this is a very helpful image for your gizmo. The energy of bonds. So remember, I can have exothermic or endothermic reactions, but every reaction requires breaking and forming of chemical bonds. Anytime I want to make a new compound, I have to break apart the old ones. So here, I want to combine my carbon and my oxygen, but in order to do so, I need to break the bonds between my oxygen atoms. Breaking those bonds requires energy. Energy is going to go into those oxygen molecules. This is endothermic. It's absorbing energy. But once I form new bonds, once I make my carbon dioxide, once those oxygens bond to the carbon, energy is going to be released. Those atoms are going to be more stable. They're going to give back that extra energy. So anytime I form new bonds, it's an exothermic process. So anytime I have an exothermic reaction, I'm getting more energy from those formed bonds than I am spending or giving to break bonds. And anytime I have an endothermic reaction, I am putting more energy into breaking bonds. My bonds are absorbing more energy than my newly formed bonds are giving off. So more energy is going into that reaction than is coming out of it. So that's all the notes that we took in class today. Remember, you need to finish your Feel the Heat gizmo. It's mostly just setting up reactions, making observations of what you notice, and answering questions about that. What conclusions can you make? What are you noticing? So I'm very confident with your notes to help you out. You'll be able to do it pretty easily. These are due on Thursday and Friday. Remember, as long as it's in on the day that it's due, I count it as on time. We may have a checkpoint opened up on Thursday and Friday, so just be prepared. We do have a little bit more notes, and I might give you some time in class to finish up on this gizmo, but that's not quite a promise, guys. Finish it if you can. If you have any outstanding checkpoints, please get those in. I know a few students are still stuck on the stoichiometry checkpoint. If you're having trouble, please come in to see one of the chemistry teachers. There's quite a few to choose from in our department. We are more than happy to go over some practice with you. If you come and see me, we will go over your old questions since you're very unlikely to get the same ones on your next quiz attempt. We'll work through it and you'll do much better. Same thing with that double replacement lab. That was also due today. Make sure you get that one in if you haven't. And if you're having trouble, please come and see me. I have some more practice problems to work on. The more you try these sorts of things, the easier they get. I know chemistry can feel pretty hard at sometimes, but we just need to practice. Well, until I see you guys again, please be safe and make good choices.